Okay, hey Aubrey, we are starting 12-1. I gave you these notes earlier today. You should have page 715. Write this down, 1 through 10 all for homework, and then 12 through 20 evens for this guy. 1 through 10 all, or excuse me, yeah, 1 through 10 all, 12 through 20 evens. Got it? Okay, just wait. You can get one here in a bit. All right, got it all down? All right, let's start. Sample spaces, not actually calculating probability. There will be not really numbers or calculations involved in today. Got it? Okay, they're just overviewing stuff for us, okay? So we've got stuff in probability called an experiment. That would be like rolling a dice or flipping a coin or selecting a student. That's an experiment. And then we have an outcome, okay? Usually when you're calculating probability, it's the number of favorable outcomes over the total number of outcomes. So if I'm rolling a dice and I want to know even numbers, 3 even numbers on a dice out of, what? Out of all, which would be 6. So 3 out of 6, 1/2 is the probability of even. Okay, got it. Sample space is just listing out. That's what today is about. Sample space, listing out the number of possible outcomes. Got it? Okay. And then we have finite sample space and infinite sample space. Okay. And this is going to depend on how many times we're doing the thing, right? Am I rolling the dice once? Am I rolling the dice twice? That is finite. Circle that. If it's infinite, if we are rolling the dice until we get a 2, like in Yahtzee, sometimes you'll try to roll until you get a certain outcome, okay? Infinite means I don't know how many times I'm going to roll it. I'm just going to roll it until I get a 2, right? Okay? So we'll talk about that later on when we categorize stuff. All right, here we go. Here is a very weird spinner, right? Half of it's purple, and then we got a red and a blue. Spinning the spinner, our sample space is red, blue, purple, okay? Even though the purple is the bigger section, we just list them out, right? Sample space is just listing them out. We're not calculating the probability of getting purple, anything like that, okay? Circle or box or do something, that is what the sample space is for that spinner, okay? If I toss a coin and I only toss the coin once, I could get heads or tails. So write this down. 1 toss, heads, tails, right? Okay, let's talk sample space. If I do 2 tosses, yeah, okay. I could get heads. I could get heads, tails. Is tails, heads the same thing as heads, tails? Nope, because order does matter. And then tails, tails. So I have 4 different possibilities, right? Okay. If we do 3 tosses, our list is going to get pretty long. But do you know how many combinations there are?
Oh, factorial.
No, it's not a factorial. Not quite. But I could get heads, like heads, tails, etc. How many is in that list?
9. 6.
Nope. It's more than 6. It's less than 20.
8.
Okay, let's talk about this. 1 toss, I could get a heads or a tails. That was 2 different outcomes, right? 2 tosses. 1, 2 tosses. How many different outcomes could this one be?
Oh, 2 times
2. This one could be 2 as well, which makes 2 times 2. That's 4 different possibilities. If I'm tossing the coin 3 times, I have 3 outcomes. 1, 2, 3.
6.
2 times 2 times 2, which is not 6.
No, it's 8.
8. There are 8 different lists in here, right? Okay. Got it? You see how that works?
So it's squared.
Okay. So if I'm tossing it 4 times, how many outcomes? 8 times another 2, which would be 16. There's 16 in that list. Heaven forbid we actually have to list those all out, right? But that's how you figure out how many, okay? And because heads and tails is 2 different options. Good question.
Is 1 a prime number?
No.
Okay.
We'll talk about that, okay? So 2 different outcomes. And then how many times you're doing it, you're just multiplying those together. Got it? Okay? All right. Let's go down to example 1, listing the sample space. 1 is done for you. What is the sample space of the experiment if you are tossing a dice once? 1, 2, 3, 4, 5, 6. They use the little curly Q brackets. Do you know how to make those? Zip. Ugh, that was really bad. You start and you do something like that. Okay? It's like an S and then a backwards S. Yeah? Just do the best you can. When I get in a hurry, mine just like turn into squiggles. Whatever. Okay? A curly Q bracket. Yes. Yes. So that we know you're not doing like an ordered pair. Don't use a parentheses. You're leaving?
Yep.
Okay. I'm recording. I'll send. Okay. 1 through 6. in the curly Q brackets, that's the list of possible outcomes for this dice being rolled, right? Okay. What is the sample space of rolling a prime number? I want you to put off to the side over here prime numbers because we got to review that. Prime numbers.
1, 3.
Now hold on.
13, 17.
Some textbooks used to say that 1 was a prime number.
Is it though?
No. What is it called if it's not prime?
Prime.
Composite. Composite. 1 is neither prime or composite.
What is it then?
It's neither. It's just 1.
That makes
Yep.
sense.
1 is neither prime or composite. So, prime. What makes it a prime number?
If you can only divide it by
If you can do
Only 1 and itself go into it.
like 1 in 17, 1 in 30, no, 1 in 30.
Yep. Only 1 and itself goes into it. Okay. The only even prime number is
2.
2. Because only 2 and 1 go into 2, right? And then we have 3. And then we have 5. And then we have 7. And then we have
11.
not 9, 11, and 13. But not 15, 17. We could keep going, right? Only 1 in itself goes into it, right? Only 1 and 3. Only 1 and 5. Only 1 and 7, right? Okay.
Every 2, I think it is. You skip the
Yep,
next one.
yep. There's like a pattern to it, right?
I thought so.
But then every, like, third one you skip, I don't know. Yeah.
Yeah.
Because then it could be divisible by 9 or whatever. So anyway, okay, prime numbers. So remember that for your homework assignment. Prime is this list and it continues on, but 1 is not a prime or composite number. Okay, remember that. All right, so we want to know rolling a dice, what's the chances or what the sample space of rolling a prime number on a dice? First prime number is 2. Second prime number is 3. Third prime number is 5. So there are only 3 prime numbers. We're listing the sample space. Now, in the next section, they will ask what's the probability of getting a prime number? 3 out of 6 or 1/2, right? Okay, but we're not there yet, right? We're just listing all the possible outcomes. Okay, go to example 2. Next page. Okay, Kemby is this person's name, has a black hat and a red hat. Okay, circle those 2 possible outcomes. Black, red. He chooses 1 hat for each day, but there's 2 days, Saturday, Sunday. So I'm going to underline those 2. Represent the sample space for this experiment. Okay, so he could wear a red hat on Saturday and a red hat on Sunday. Do you see this down here?
Yep.
Red hat. Or he could wear a red hat on Saturday, blue hat on, is it blue? Black hat on Sunday, right? So red, black is a combination. Black, or what's the? Black, red. That's the one we're missing, right? Okay. Now, there are 4 combinations here. How do I know that there are 4 total? 2 hats, 2 days. 2 times 2 is 4, just like we said before, right? Okay, so that's how you can know if you got them all listed, right? How many outcomes for each day? There's 2 days, 2 slots, 2 each day. So multiply together gives you 4. Got it? Okay, all right, so now they have it listed as a table. So I have a red and a black for Sunday. I have a red and a black for Saturday. And if I match them up, red and red cross at red, red. Red and black cross at red, black. This is a table, okay? This one would be black, red, and the other one's black, black. Got it? That is doing the same thing, but instead of making an organized list, which is what this is called, okay, this is a table, all right? Then we have a tree diagram. Ready? Tree diagram. This is your first day. This is day 1, so probably Saturday. This represents day 2, okay? So day 1, I had 2 options. Now day 2, it's not that day 2 has 4 options, but given that I did red on the first day, I have to have a red-black combination on the second day and a red-black combination on the black option for the first day. That was confusing. Do you see why the second level has 4 outcomes, right? So that when I follow this tree diagram down, I have red, red, which goes here. I have a red-black combination, which goes here. I have a black, red, right? And I have a black, black. So this should be black here, down here. Okay? That is your tree diagram. Clear as mud?
Yep.
Sure.
Yeah? Good? Okay. All right. Okay, let's go down to example 3, next page. Flip over. All right, this is where it gets a little confusing. infinite and finite and discrete continuous. Okay, so here we go. Circle these, infinite, finite. I'm going to talk to you about classifying these, infinite or finite, okay? You're categorizing these scenarios of what you're doing, like rolling the coin, rolling the dice, flipping the coin, choosing a student, whatever, right? Finite or infinite means, is it a set number of times that I'm doing it? Or is it like until I roll a 6? Or until I choose a 7 in cards, right? Okay, so set number means it's finite. Infinite is until something happens, right? Until get desired outcome. Does that make sense? So maybe let's just start there. Let's go and categorize these three ABC as finite or infinite. Yeah? Okay, A marble is drawn from a bag that contains three orange marbles, 5 green marbles, and 4 blue marbles. Okay, how many are we drawing?
12, 13, 12.
How many marbles are we drawing?
Whoa.
1 marble out of 12, right? Okay, but I'm only drawing a marble. Finite or infinite? Finite. This one's going to be finite. Okay, all right. Okay, you do BC. Finite, infinite. Write them out. See what you get. Hold on. Just write it down. You do BC. Just read it real quick and just do finite, infinite. Finite, set number of times, infinite until they get the desired outcome or whatever. If it goes on forever, it's infinite. Okay. All right, B. A spinner with 4 equal parts, green, blue, red, and yellow is spun until it lands on yellow. Finite or infinite? Infinite. I don't know how infinite. I don't know how many times it's going to be. I could end up rolling that thing forever. I probably won't. I probably will land on yellow at some point, but I could end up rolling it forever. Okay, what about C? A ball is thrown into the air and its heights are recorded in inches.
Infinite.
Yeah, I have no idea how many times I'm doing it, so it's going to be infinite. I could be until I get 12 feet high on the nose. I don't know. Infinite. Got it? Questions about finite, infinite. Now we've got to categorize as discrete or continuous. I think we've heard those words before. Discrete or continuous. Discrete means countable. Continuous is usually represented as decimals that go on forever. Right? So like temperature. It might say 98.6 degrees on your thermometer, but that's because it rounds it, right? It's actually probably 98.614375289 and on forever, right? That decimal continues on forever, right? It's just your thermometer rounds it off, right? My bathroom scale rounds to the nearest like quarter of a pound or something like that, but I'm probably not exactly on the nose quarter of a pound, right? I might be like 0.7143 of a pound. I'm not going to tell you what the first number is, but the decimal on the end, right? Okay. So, discrete, continuous. All right, a marble is drawn from a bag that contains 3 orange marbles, 5 green marbles, 4 blue marbles. I'm doing a finite number of times I'm drawing. Is it discrete, countable, or are we dealing with decimals that continue on forever? Discrete. So it is finite and discrete. There you go. Okay, B. Spinner with 4 equal parts, green, blue, red, yellow, is spun until it lands on yellow. Infinite number of times, but discrete or continuous? Discrete. Okay, what about the third one? A ball is thrown in the air, heights are recorded in inches. Yeah, because we could say a half an inch, or we could say an eighth of an inch, or a 16th of an inch. I don't know what I'm rounding to. That could be a decimal that goes on forever, so continuous. What? 1/9 of an inch. Nobody goes ninths of inches. Sure, I guess you could, whatever, right? Infinite, continuous. Do you see how the different combinations could be? Yeah? Finite doesn't always go with discrete, because this one's infinite discrete, right? Okay, you could have different combinations. All right. Last thing that they address here is something called the fundamental counting principle. You guys have had like on maps testing before, possibly, where they say you have 4 pairs of pants, and you have, and you have 6 shirts, and you have 2 hats. How many different outfits, right?
48.
How do you do that? 4 times 6 is 24, times 4 is, or times 2 is 48, 48 different outfits, okay? It's kind of like at the beginning when we were talking about if you have 2 coins, this one could be heads or tails, and this one could be heads or tails. That's the fundamental counting principle, 2 times 2. Or if I'm flipping it 3 times, I get 2 times 2 times 2, right? That's the fundamental counting principle. How many outcomes you're taking it times how many times you're doing it, right? There's 3 categories, but I have this many combinations. You just multiply them all together. That's what fundamental counting principle is. Got it? 48 for that one. 48 outfits I could do, right? Okay? So if you're talking tree diagram, you want to see what this tree diagram would look like?
Do we have to make
Gross. What?
We have to make these on the homework.
I don't know if it says to, yeah. We had 4 pairs of pants, 4 pants, 6 shirts, and 2 hats, right? Here's what your tree diagram would look like. Don't write this down. You don't have to write this down. I'm going to start with 4. 1, 2, 3, 4, right? Maybe I'm wearing jeans, leggings, slacks, black slacks, and a skirt. I don't know. Those are my pants, right? Okay. And then within those, off of each one, I'm going to do how many? 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, etc., right? And then off of each one of those, I'm going to do 2 more, right? So on this lowest level, how many will there be? 48. Yeah? And you can see why, right? Like it ends up multiplying pretty fast. Got it? All right, fundamental counting principle. We have Santiago lists the number of sections available for the courses he will take in his first semester at college. How many different schedules could he take? So there are 6 different sections of art history. Wow. Like that would be nice for like Mrs. Cleaver to have that many sections when she goes to put you guys into slots, right? Versus one section for geometry you have to take at 8th period, right? Bah. Okay. All right. 6, 5, 9, 4, 6. What are you doing? Multiplying them all together. How many different class schedules could you have if you multiply them together? 6 times 5 times 9 times 4 times 6.
6,480.
6,480. Holy cow. That's how many different class schedules you could have.
Let's write that out.
Woo! You want to list them all out?
Yep.
Okay, real quick. Zach, a little bit ago, talked about factorial. What is a factorial? We'll talk about this tomorrow. Not tomorrow.
Itself by itself.
What?
It's like 6 times. That
So if you're talking 6 factorial, what does that mean?
6 times 6 times 6
Nope.
times 6.
Nope.
6 times 5 times.
Yeah, 6 times 5 times 4 times 3 times 2 times 1, yeah?
Oh, it goes down.
Okay. What's a scenario of when you do 6 factorial? Like, how does that even work?
You
You choose
lose,
something out, but then you don't put it back in.
you lose something. every
Right,
single
kind of. Okay. All right, let's say I have 6 players in baseball, and I want to figure out how many batting orders I have, right? 1, 2, 3, 4, 5, 6. How many players could be in that first batting order? Like 6, okay? But one person's already chosen, and it is Wyatt. Wyatt gets chosen first. Now, Wyatt cannot get chosen in the next category, right? So how many people could be second in the batting order? 5. How many people could be chosen third? Does this make sense? That's when a factorial comes into play. Make sense? We'll get to that, I think, tomorrow when we do counting. Got it? Yeah?
720.
Oh, we're not in here tomorrow. Not tomorrow. Wednesday. Wednesday?
Wait, why are we not in here?
Because we're doing that.
I thought we were in here first. Is this
No,
for-
no. So the deal is we go 1st through 6th period,
Yeah.
Friday schedule. Then we go to lunch. Then back from lunch, you leave to go down to Red Cloud. And then you go to 7th period when you're done and no 8th period. Is that true? Yes. Okay. Yes.
Who do you guys want to ride with? Sophomores? You guys want to be with the 6th graders tomorrow on the same boat?
I choose juniors.
We don't choose.
I'll have the buses.
We don't
figured out.
want
I have
you
to
to
look at how many can fit on the bus.
How many kids are in each one?
4:30.
Well, you guys are a big class, sophomores, and juniors are a small class. So, like the numbers, you know, whatever.
We don't need to bring that up.
Seniors are mid-size. They're not as big as sophomores, but bigger than juniors, right?
And
I
we
see
have like
juniors and
30.
seniors and sophomores get their own
That'd
bus.
be almost-
Sophomores get their own bus because they're so big. How many buses are you taking?
No.
Four?
like, or-
Four?
Yeah, too much.
Yeah.
Be almost
They might have to
30.
split some
You
classes
could do
out.
an assignment for the probability. What would the probability be of the sophomores and the juniors based on numbers,
Right,
based on each bus?
right.
You guys can figure it up for a homework assignment.
Sure. That sounds awesome.
Only if we get our own bus.
Yeah.
How many are there in the bus?
30.
Oh, you put them in five.
So you
Nice.
probably wouldn't
Is
be
that
the
counting,
sixth graders,
Carmen?
'cause there's 25 of them.
Is that counting?
What? I'm not going.
Because there's 30 of them,
Carmen.
right?
Oh, I thought you said Comey. Good heavens. Okay, I'm gonna shut this video off.